So what we are going to do is give you an alternative way of multiplying complex numbers. Okay, and that alternative way uses the polar format of complex numbers. So yesterday, I think we started class with like a 2 plus 3i, and I asked you to multiply that by like 4 minus 5i or something like that. And we went through and we did that, and we had to FOIL. We did the whole, first times first, outside times outside, inside times inside, last times last thing. We go last times last, we get an I squared. So it turns into negative 15i squared to a positive 15. Then we condense by combining like terms, and we have then the complex number that is generated by that product. Now, what we're going to do is the same thing, but do it in polar form. And what happens, and hopefully we can show and demonstrate, is that doing it in polar form, multiplying complex numbers in polar form, is such a more efficient process than multiplying them in rectangular form. Okay, so here is kind of the breakdown of how we're going to go through doing this. It says if two complex numbers z1 and z2 have polar forms, r1 cosine theta 1 plus I sine theta 1. And yesterday I said that this is equivalent r1 cis theta 1. Okay. You might see me, because I don't want to write all this stuff out because I think it's cumbersome, time consuming. So I'm going to use r cis quite a bit, but we need to make sure that we understand that it relates back to that. You get to a college level course, obviously this is college level, but you get on campus somewhere, probably 9 out of 10 times they're going to use r cis and not this. Okay, so I think that notation is important for us to know. Over here, obviously, z2 we can rewrite as r2 cis theta 2. Okay. It says then if I want to multiply these things, z1, z2, then all I have to do is take r1 times r2, and I've got my cosine, my cis part, cosine plus I sine. But look at the arguments, you're adding the arguments together, right? Okay. This will look, using the cis format, it would look r1, r2, cis theta 1 plus theta 2. Okay. Again, that's kind of the preferred technique that I'm going to use, especially if all they want is the product to be left in polar form, then that's really easy and I'm done. Okay. If they want me to rewrite it in a rectangular form, then I'm probably going to expand it to the cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2 and evaluate that way. If we want to multiply two complex numbers in polar form, you just multiply the moduli and you add the arguments. Okay, multiply the moduli, add the arguments. And we can really do that, if that multiplication occurs for z1 times z2. Okay, what if I had a z3 and I go z1 times z2 times z3? It's the same concept. Multiply all your moduli together, add all your thetas together, all your arguments, and you should then have that thing in polar form pretty quickly. Okay. If I want to divide them, okay, division, you got to be careful with division because division is not commutative like multiplication and addition are. So when I do z1 divided by z2, that is a different answer than z2 divided by z1. Obviously, we know 2 divided by 3 is different than 3 divided by 2, right? So the same commutative issues occur in the complex plane. But following kind of the same principles as multiplication, if I'm going to divide complex numbers, I divide the moduli. Order matters now, okay? So z1 over z2, then means r1 over r2. If it was z2 divided by z1, it'd be r2 divided by r1, okay? So make sure we understand the subscripts are important here. Okay, these are all ones up top, 1, 1, okay? And then in the cis part, my thetas, I'm going to subtract them. And again, subtraction order matters, right? So you see theta came first in Z1 over Z, or sorry, 1, the subscript 1 came first in Z1 over Z2. It came first in R1 over R2. It comes first in theta 1 minus theta 2. Okay? So just be careful when we do that. For instance, I guess what I'm trying to say here is when I want something like maybe Z2 over Z1, that is going to look like R2 over R1. Cis, that would be theta 2 minus theta 1. Does that make sense to everybody? Okay. Division order matters. You got to pay attention to that. Okay. Z2 cannot be 0. 0 is a complex number. 0 plus 0i exists in the plane. Okay. It's the intersection of the real axis and the imaginary axis. But when we do division, just like division in the real plane, you can't divide by 0. Okay. But dividing complex numbers in polar form, you divide the moduli in the order that is defined, and you subtract the arguments in the order that is defined. And ultimately, guys, that is much faster than doing any multiplication or division in rectangular form. If you think about rectangular form, division for complex numbers, I don't know if you guys remember doing this. We did it a couple times earlier in the year. I know you spent a lot of time in Algebra 2 doing this. But if I want to, let's go to this slide here real quick. If I have like 3 plus 4i divided by 2 plus 5i, and I want to divide those, you guys remember how you do that? You actually multiply by the what of the bottom, conjugate, okay? Now, this is multiplication by 1, right? But when I multiply by that conjugate, divided by that conjugate, it's going to take the I out of the denominator, and this it turns into, because how conjugates FOIL, that's going to turn into a real number, and you're left with now multiplication up top, and that's going to leave you with an A plus BI up there, and you end up getting the quotient of those two things. That's an elaborate process where if we're doing this in polar form, that is much quicker and easier to deal with, okay? So I'm going to do 2 examples of this. I'm going to let Z1 equal 3 cis pi over 3 and Z2 be 2 cis pi over 6, okay? So my R1 is 3, my R2 is 2, theta 1 is pi over 3, theta 2 is pi over 6, okay? Using what we just talked about, if I want to find Z1, Z2, it is R1, R2, cis theta 1 plus theta 2. So R1, like I said, was that number there. R2 is that number there. And then I go cis pi over 3 plus pi over 6. And it gives me 6 cis. Now pi over 3 plus pi over 6 is pi over 2, right? Okay, this would be 2 pi over 6 plus 1 pi over 6. So now, you know, I could be, if the question was just find the product and leave it in polar form, this is the product in polar form. That is the solution, okay? Now, if they wanted it in rectangular form, you do this. Kind of expand it, and you don't have to necessarily write this. I think the more examples you do, the better you would get at this and realize that this means 6, the C means 6 cosine pi over 2, and this IS means 6I sine of pi over 2. And you might be able to kind of keep that stuff straight in your head. I think it's safe right now, or safer right now, to expand it. What is cosine of pi over 2? 0. What is sine of pi over 2? 1. So 1 times 6i just gives me 6i, right? So the product of these things is 6i. Now, here's kind of where this would, maybe the purpose of this would be, if z1 is that, I'm going to rewrite z1 as 3 cosine of pi over 3 plus 3i sine of pi over 3. What's the cosine of pi over 3? 1/2. So 3 times 1/2 is actually 3/2. And then the sine of pi over 3, the radical 3 over 2, right? So this becomes 3i radical 3 over 2. That is the rectangular form of z1. I want to do the same thing for z2 real quick. I'm just trying to prove a point here for you guys. Okay, so cosine of pi over 6. Cosine of pi over 6 is radical 3 over 2, right? Multiply that by 2, you get just radical 3. Sine of pi over 6 is, what's the y value of pi over 6? 1/2. 1/2 times 2 is just 1, right? So there is the rectangular form of z sub 2. Okay? When I ask what z1, z2 is, and we did it there in red, it is the same thing as asking what is 3/2 plus 3i radical 3 over 2 times radical 3 plus I. If you had to FOIL that, can you imagine just kind of the messy nature of that thing? Okay? And if I FOIL that, we find out that it turns into 0 plus 6i. It's just a messy procedure in doing that. If I go 3/2 times radical 3 gives me 3 radical 3 over 2, so that's first times first. I'll do outside times outside, so 3/2 times I, plus now the inside, so it's going to be 3i times 3. Okay, let's see here. Cursor died. It's just going to be, I'm just going to write it kind of deliberate here. 3i radical 3 times radical 3 all over 2. That would be that term times that term. And now I got to do last times last, so it'd be 3i squared radical 3 over 2. Okay? What's this I squared turn into? -1, so there's a negative. So now, do you see that this 3 radical 3 over 2 and this negative 3 radical 3 over 2, they're going to wipe each other out, right? Okay? What is radical 3 times radical 3 going to give me? It's going to give me 3. Okay, so now up top, I get 9i over 2, right? So we have 3/2 I plus 9/2 I. What's 9 plus 3? 12. Right, 12i over 2, which is 6i, right? Is that the same thing we found right there? Okay. But the idea is, if I do it in polar form, so if they were to give me this information at the onset, this was maybe the start of the problem, and they say multiply 3/2 plus 3i radical 3 over 2 and radical 3 plus I, it's probably easier to go take that number and make it into that, take that number and turn it into that, and then do the work in red. Does that make sense? Okay. Especially when the numbers start getting really ugly. Okay. The polar form of multiplying, dividing these things is intended to be an efficient process. Okay, and much more efficient than our foiling. If I want to do z1 divided by z2, z1 divided by z2, that's going to give me, I take my r1 divided by my r2, so it gives me 3/2. And then I go cis, and now I'm going to take pi over 3 minus pi over 6. Okay. Pi over 3 minus pi over 6, just pi over 6, right? So we get 3 halves, cis, pi over 6. And that's my answer in polar form. If I want it in rectangular form, I'm going to do this. And then just evaluate. What's cosine of pi over 6? Radical 3 over 2, so I get 3 halves times radical 3 over 2. And sine of pi over 6 is 1 half, so I get 3i over 4. So this becomes 3 radical 3 over 4 plus 3 over 4i. And that would be the answer in rectangular form if desired. Which that is a lot easier. And if I go back and I erase them, I shouldn't have, but if I go back and I look at what Z1 and Z2 were in rectangular form, okay, and I ask you to divide those, okay, you're going to have an ugly quotient, and then you're going to have multiplication by an ugly conjugate, okay, and it just gets nasty, okay, well, that is much quicker to do right there, okay. And as you go through homework assignments, you go through tests and quizzes and general practices, they'll ask you, do this multiplication using FOIL, okay? And then they say, okay, now do the exact same problem using polar form. And they ask you to kind of realize, do you come to a conclusion a lot quicker in one of these formats, in one of these processes? And usually the answer is yes, I do, and the polar form is easier. Okay? That gets us into what we refer to as the Moivres theorem. Okay, the Moivres theorem is actually that idea, but it deals with replication of, repeated multiplication, doing the same multiplication over and over again. So it says repeated use of the multiplication formula that we just talked about gives the following useful formula for raising a complex number to a power of n for any positive integer n. Okay. So before we get into kind of defining the Moivres theorem, kind of give you an example of what I'm talking about here. If I say z is equal to like 2 cis of, I'll just go pi over 4 and make it easy, I guess. And I ask you find z to the 8th. Does that mean I'm taking, and let's not do to the 8th because that's going to, I don't want to write all that out. Let's go z to the 4th. Is that the same thing then as taking 2 cis pi over 4 times 2 cis pi over 4, 2 cis pi over 4 times 2 cis pi over 4? Does that make sense? Okay. Now, using the multiplication rule, here's R1, here's R2, here's R3, and here's R4. So I'd write that as 2 times 2 times 2 times 2, right? But what can I rewrite that as? 2 to the 4th, right? And then I could have cis. Now here's theta 1, here's theta 2, here's theta 3, and there's theta 4. I'd have pi over 4 plus pi over 4 plus pi over 4 plus pi over 4. When I do repetitive addition, that's the same thing as what? Multiplication. So I would take pi over 4 and multiply it by 4. And now what happens is I get 2 to the 4th ends up being 16. And I get cis of pi. And now it's 16 cosine of pi plus 16i sine of pi. And that should be, what, negative 16 there. Cosine of pi is negative 1. Sine of pi is 0. It just gives me negative 16. Okay, if I were to take that number right there, and multiply it by itself 4 times, you get negative 16. Okay? De Moivres recognized that this is a pattern. Okay? This happens all if I want to go z to the 5th, okay, then I have one more 2 to multiply by my r to the 4th already, or my 2 to the 4th, and I would have one more theta to add in there. Does that make sense? So De Moivres says if you're going to raise a complex number to some power, okay, if I'm going to take r cis theta, I'm going to raise that to the nth power. Because of the multiplication rule, it just simply turns into r raised to the nth cis n theta. Okay? That's all we have to do. He also has a second component to his theorem, which deals with roots, which is actually something that's maybe not as obvious as what we just did here. This is just an extension of multiplication. Tomorrow we'll talk about how to take like the square root of a complex number, something you've never done before, or the third root, or the fourth root, or the fifth root, which is a great use of De Moivres' theorem. Okay. So that's what I was talking about the other day. If I have something like, let's go back to 2 plus 3i, and I want to raise that to maybe the 10th power, we talked yesterday that you'd have to write that out 10 times, right? Okay, you'd have a bunch of foiling to kind of mess with. Okay, well, what De Moivres says is turn 2 plus 3i into polar form, and then apply that rule. That kind of makes sense? Okay. So we'll do an example of this, and it does make things very efficient for us in regards to some of our calculations. All right. So the example I want to do is this one. It says if z is equal to 2 minus 2i, I want you to find z to the 8th. Okay? 2 minus 2i, I want to find z to the 8th. And what I want to do right now, guys, just humor me, because I think it's something. 8 is not a terribly large number because it's even. I think some of our foiling here is going to be really nice. Let's write this out using rectangular form. If I go 2 minus 2i to the 8th. Now, I think I'm going to try to be intelligent about this. If I have something, let's say I take z squared, and I raise that to what power is the same as z to the 8th? Should be the 4th power, right? So if I wanted to do this in rectangular form, let's just figure out what that looks like first, and then we'll raise that to the 4th power. So what is 2 minus 2i times 2 minus 2i? Well, if I FOIL, 2 times 2 is 4, right? I'm going to get negative 4i and another negative 4i, so negative 8i. And then negative 2 times negative 2 is positive 4. And then I squared. That turns into a negative, and I'm left with just negative 8i, right? Does that make sense? Okay. So that is negative 8i, and I want to raise that to the 4th power. So now it's going to be negative 8i times negative 8i times negative 8i times negative 8i. Okay. And this turns out to be, so negative 8 times negative 8 is 64i squared, right? And this thing will be 64i squared. So it's actually negative 64 times negative 64, right? And that turns out to give me 4096. Okay? So that is what this thing raised to the 8th power should look like. And that's using rectangular foiling. Does that make sense? Now this one was a little bit more convenient because when I took 2 minus 2i times 2 minus 2i and I squared that, this here occurred where my real parts kind of cancel each other out, right? That won't always happen. So that negative 8i could end up being, maybe 2 plus 8i or 2 minus 8i, and I want to FOIL that. It makes the process a little bit longer. Does that make sense? Okay. just the relationship between my a plus bi and a plus bi here providing me additive inverses. That won't always happen. So let's see if we can get the same answer using de Moivres. Okay. Now what you have to do, I'm going to use de Moivres theorem. This is in rectangular form. I need to convert it to polar. Okay. So remember polar form. We talked about this yesterday. You need your r, which is going to be the square root of a squared plus b squared. And the hopes are is that is something that we can quickly do. Okay, that's kind of mental math there. 2 squared plus 2 squared, right? So it's going to be radical 8. My suggestion to you, don't rationalize. Some nice things are probably going to happen when we raise this thing to a power. Theta, remember tangent inverse of b over a. So that's tangent inverse of negative 2 over 2. So that's going to give me tangent inverse of negative 1, which ends up giving me negative 45 degrees. Okay, you want to use negative 45 degrees, that's okay. I would probably prefer maybe 315 degrees or in radians 7 pi over 4. Those are coterminal with negative 45. And that should make sense if I look at just a quick, having an image of this thing in my head real quick. 2 minus 2i would be that point right there. So it is, you know, a pretty large angle. It's over 270. So it should be in the fourth quadrant. So that makes sense. So now z in polar form is going to be radical 8 cis. Let's just use, I'm going to use 7 pi over 4. It does turn out to be a pretty nice thing if I use 7 pi over 4. So that's z. Does that make sense? That's the polar form of that. All right, so if I want to find z to the 8th, de Moivres theorem says all you do is you take z, raise it to the 8th power, and that turns into, you raise your r, or your modulus, to the 8th power. You write cis, and then you take your theta, or your argument, and you multiply it by 8. Now, this is the reason I told you not to rationalize the radical 8. Radical 8 is the same thing as what in regards to maybe a fractional exponent? Square root is the same as raising something to what power? 1/2 power. So when I have the square root of 8 raised to the 8th, that's the same thing as 8 to the 1/2 raised to the 8th, and 8 raised to the 1/2 raised to the 8th. What do I do with those two exponents? Multiply them. So I get 8 to the 4th. And if you think about it, 8 to the 4th, that's 64 times 64, isn't it? Okay, so we're going to see where that 4096 kind of generates here. I then have cis, and the reason I wanted to use this as 7 pi over 4 is because that and that are going to cancel out, and it leaves me 14 pi, right? Okay, so I get 4096 when I take 8 and raise it to the 4th power. Cis of 14 pi. 14 pi, what's that the same as? 14 pi is going around, starting here, and going around the unit circle how many times? 7 times, right? And it would get me back to right there, correct? So isn't 14 pi the same thing as 0? So then I could rewrite this as cis of 0. These are all things that maybe you can do in your head. You don't necessarily need to write these down as you get better at these. But I get 4096 cosine of 0 plus 4096 times I sine of 0. What's the cosine of 0? 1. What's the sine of 0? 0. That goes away, doesn't it? Am I left with 4096? Same thing we found using rectangular coordinates, right? Now, I don't know if we were to time both processes when we did it by rectangular foiling. I don't know which one's going to be quicker in this instance, but holistically, over all examples, all questions that you'll do, polar form is quicker. Because what if I wanted to take that thing and raise it to the 28th power? Would you want to FOIL that out? No. You would rather change it into polar, take 8 to the 1/2, raise it to 28, so you get 8 to the 14th, and then take 7 pi over 4 times 28, so you get, 7 pi, times 6, so you get 49 pi, and it's a lot quicker, it's a lot easier that way. Okay. So that's a portion of de Moivre's theorem. Hopefully those examples are enough to help you kind of work through that assignment. We'll do a couple more examples tomorrow in class. Everybody here, we have a little bit more time. The assignment that deals with this is not due tomorrow. But make sure I do have 4 or 5 assignments open right now that you're paying attention to due dates and getting those things submitted prior to those deadlines.